Hello. In this video, we are going to talk about counterexamples. And so this is a method of disproof, of disproving a statement. And then we will look at a few examples. So first off, what's meant by a counterexample? Well, like I said, this is a method of disproving a statement, and statements we'll be looking at here take the form for all x in S, R of x, for some open sentence R of x. So if I want to show that this statement is false, if I want to disprove this, well, I need to come up with an example of an element of S such that R of x is false, right? We talked about this when we talked about negating these things, and really what we're trying to prove here is the negation of this, that it's not true, that it's false. So disprove will show there exists an element of S such that R of x is false. So that's our goal with a disprove, is to come up with an example such that the statement's false. This element x in S, this would be called a counterexample in this case. Now, we're also going to look at statements, and really what we really want to do here is look at statements that are implications. Because a lot of statements in mathematics are implications, and so we should talk about how do you disprove a universally quantified implication like this. So if we have a statement like, for all x in S, P of x implies Q of x, how do we disprove this? We have to remember that how to negate an implication. So remember that the negation of R of x, this would, so disprove this. To disprove this, we would show that there exists an element of S such that not P of x implies Q of x. And this is where remembering how to negate an implication comes into play. Remember that this is equivalent to P of x being true and Q of x being false. So to disprove this statement, we want to show, we want to come up with this example x in S such that P of x is true and Q of x is false. That would disprove the implication. Let's take a look at an example. So disprove the following. Let n be an integer. If 4n plus 5 is odd, then n is even. So let me break this down. This looks like the statement for all n in the integers. And let's come up with, we have P of n would be 4n plus 5 is odd. And Q of n would be n is even. So this looks like what I was just talking about, disproving an implication, right? Disprove the following. So what do we have to do here? So we're disproving this. So we need to show that there exists an integer n such that P of n is true, such that 4n plus 5 is odd, and n is also odd. Right? We assume we want to show that the hypothesis is satisfied, but the conclusion doesn't follow from it. Can you come up with a counterexample here? An example of this? N is odd and 4n plus 5 is also odd? Yeah, what about if n is 1, for instance? Let n equal 1. Then 4n plus 5 is equal to 9, which is odd, and 1 is odd. So that would disprove this statement. We did it. Yay. n equal 3 would have worked too. There's a lot of different things that could have worked here. But certainly n equals 1 works. So this is an important thing to note here, that when you are disproving something, it's important not to just give let n equal 1. If I just saw this on a homework assignment or an exam or something like that, that's not enough. You need to show me that the hypothesis is satisfied, that 4n plus 5 is odd, as we did here, and the conclusion does not follow, right? You need to show me that this statement is satisfied. So there's still some work to do with a counterexample. Let's look at another example that's maybe a little bit more difficult. So disprove the following. Let m and n be integers. The integer 3m plus 7n is even, if and only if m and n are both even. Okay, so first thing to note here is we have a biconditional that we're trying to disprove. So we're trying to disprove for all integers m and n, p of n, if and only if q of n. So here we'll say p of mn if and only if q of mn. So let's let p of mn be the statement 3m plus 7n is even, and q of mn be m is even and n is even. Then this is what we're trying to disprove. Remember that this biconditional is equivalent to p of mn implies q of mn, and q of mn implies p of mn. So in order to disprove this, I just need to show that not both of these are true, not both of these implications are true. I just have to show one of them is false. So I'm going to write down both of these implications. So p of mn implies q of mn. That would be 3 if 3m plus 7n is even, then m and n are both even. That's the forward direction. And I'll write the backwards direction as well. If m and n are both even, then 3m plus 7n is even. We're going to analyze both of these, figure out which one of them is true, which one of them is false, or just figure out the truth values of these, and then whichever one's false, we'll disprove that. So let's actually start with this, the converse, the backwards direction. If m and n are both even, then 3m plus 7n is even. So you can kind of think about this in your head. If m is even, then 3 times m will be even. If n is even, then 7 times n will be even. When I add them together, it'll be even. So this appears true. It looks like we could prove this statement. So we can't disprove this part of it. It looks like we need to disprove the forward direction. So let's write out what it would take to disprove this. So we're going to disprove the forward direction. So we need to come up with an example. There exists m and n such that 3m, the hypothesis is satisfied, 3m plus 7n is even, and not m and n are both even. So think about the negation of m and n being both even would be m is odd or n is odd. M is odd or n is odd. So I need to come up with an example where at least m or n is odd, but 3m plus 7n is even. So think about how we can do that. We can kind of run through the cases here. If m is odd and n is even, 3 times an odd number, that'll be odd, plus an even number, 7 times n would be even there. That would give me an odd number, so that wouldn't work. So it seems like if one of these is odd and the other is even, I think this will actually be true. This will be odd. So in order to disprove this, I think what we need is for m to be odd and n to be odd. And that's okay. That's still true that m is odd or n is odd. So let's try. Let m equal 1 and n equal 1. Why not? They're both odd. Then m is odd, or n is odd. That's true. They're both odd, though. That's okay. We can say m is odd or n is odd. That's still true. And 3m plus 7n here would be equal to 10, which is even. So this is my counterexample here. That's a counterexample. So a little bit trickier when we have a biconditional because we have to break it down and analyze each implication and determine which one's true, which one's false, and then come up with a counterexample for the one that we've determined was false. All right, let's do one more example here. That doesn't have to deal with even and odd. I'm probably getting sick of it. Disprove. If x is a real number, then x squared minus 2 squared is strictly greater than 0. So what does this statement look like? Well, we could write it like this. For all real numbers x in R, x squared minus 2 squared is greater than 0. So we want to disprove this. So we're going to show there exists a real number x such that x squared minus 2 squared is not greater than 0. So less than or equal to 0. So remember that if you square any real number, it's always greater than or equal to 0. So the only issue with this is that the original statement says strictly greater than 0. So if I can make x squared minus 2 squared equal to 0, that'll be a counterexample. So I want x squared minus 2 to equal 0, which implies x squared is equal to 2. And so we would have x equals square root of 2 or x equals negative square root of 2. Both of these would be counterexamples. So let's disprove this. Let x equal square root of 2, then x squared minus 2 squared is equal to square root of 2 squared would be 2 is equal to 0, which is less than or equal to 0. That disproves the original statement, which claimed that any real number, we'd always get something strictly greater than 0. Okay, that's it for this video and for counterexamples, disproving statements. See you next time.